undertaking of regular, generally what is called cardio exercise. In other words, moderate to low intensity, rhythmic muscle contraction type activities that last for a significant period of time. Why that is a bad idea, why we shouldn't be doing that, how that impacts on your physiology, and sort of just to start pointing you in that direction so that you can start doing some research into that for yourselves, if that's of interest to you. So without too much more ado, let's carry on there. Basically, just to review from part one, if you haven't seen part one, I'd suggest that you actually do go and view part one. It will give you the background that I'm kind of referring to very quickly, very loosely here, just to sort of get your mind back on track. This is not a substitute for watching part one. You need to watch part one, but here's a brief sort of review of it. Basically, what we spoke about in part one was that when a muscle fiber contracts, there is a vast step change in the requirement of ATP to power that muscle twitch, that muscle contraction. That's orders of magnitude in terms of the requirement from resting to contraction state. That step change occurs within 10 to 40 milliseconds, so very, very rapidly. Whether it's 10 or whether it's 40 depends on the muscle fiber type, which is what we're going to talk about in this video a bit. The type 1 fibers generally tend to be at the lower end of that range, and the type 2A and 2B fibers, sort of 2A intermediate and 2B fibers at the quicker end. We'll talk about this a bit more when we talk about fibers. There are different categories of muscle fibers. They're not really categories, it's more a continuum, but we'll talk about that when we get to it. So we'll cover that later in this video. The step change in ATP requirement actually can't be subserved by a step change or rapid increase in the oxidative phosphorylation rate. The reason that's impossible is because that oxidative phosphorylation rate, the mitochondrial function rate, has massive inertia. It takes about 3 minutes actually to get your system to speed up to a new level of requirement. 3 minutes is a lot longer than 10 to 40 milliseconds, as I'm sure you'll agree. That's therefore impossible. So the oxidative rate rolls along at a rate that is averaged out across time in order to subserve the overall energy requirements of the cell, but certainly not to subserve the requirements of ATP during the actual contractions themselves. So that is subserved by another temporal energy buffer, if you like, or time buffer. That's glycolysis, the splitting of sugars. It's actually glycogenolysis to be accurate. It's glycogen that is cleaved in muscle fibers that's energetically favorable to glucose. So a lot of ATP is made very, very rapidly for muscle contractions that way. Pretty much a single muscle fiber contraction, a single muscle fiber twitch, even at very low intensities, which I'll talk about a bit later in this video. Basically, that would drain the muscle fiber entirely of ATP, and so that's why we have oxidative phosphorylation, to average that out across time and to supply the energy for the resynthesis of more glycogen, so that we don't basically run out of ATP, pretty much. And in order to communicate and shuttle the energy between the mitochondria that are in one part of the cell to the contractile proteins within the muscle fiber, we need a spatial buffer. That's the phosphocreatine system. So basically, the take-home message for part one is that we're often taught about there being 3 discrete energy systems. There's actually 4 if you count a thing called the adenylate kinase system, but that's a bit advanced and beyond the scope of this discussion, so we won't go there. But what I'm actually suggesting is there isn't 3 or 4, there's 1. They're gears in the gearbox, they all rely on each other. If any one of those systems fails, the muscle fiber fails, you don't have the ability to exercise either aerobically or anaerobically, as we're taught. That's absolute ridiculous nonsense. All muscle fibers require oxygen glycogen and phosphocreatine systems running, as well as the adenylate kinase system actually, but that's another story for another day. So all of them are gears in the gearbox. Basically, we have one integrated energy system, not three or four. We don't have aerobic systems and anaerobic systems. We just have our system, which relies on all its components, both those that use oxygen directly and those that don't. So we are oxidative animals. If you have any doubt about that, just hold your breath for about 5 minutes and we'll see how that goes for you. Then tell me all about your anaerobic abilities after that, which you actually won't be able to do, obviously, because you'll be dead. So, yeah, that's pretty much that one in a nutshell. That was part one. Let's move on now to part two so that we can cover what I need you to understand from today's chat. I want to talk about muscle fiber activation, or muscle fiber recruitment, it's sometimes called. How does that work? Look, I'll just give you a really brief, really basic rundown on that. Basically, in the resting state, if you like, muscle fibers maintain either elevated or depressed levels of different ions, depending on which ion it is. Sodium in, potassium out, chloride and other ions as well in and out. Basically, what we have is a situation where we have inside the cell we have certain ionic concentrations, outside the cell we have other ionic concentrations. They're prevented from equalizing across the membrane by the membrane having closed gates, if you like. When a muscle fiber receives a nerve signal that it's time to contract, which is called twitch, that basically opens gates in turn in sequence along the length of the muscle fiber that allows those ionic concentrations to equalize themselves according to their concentration gradients. And it's the process events around that which causes the contractile proteins actin and myosin to basically be able to do their work and to contract. The way that works is around the release of calcium ions, which are sequestered in a sac, if you like, called the sarcoplasmic reticulum, if you must know, during rest. And when a message to contract or to twitch is received, the calcium ions are released from that sac via an effect which is due to that ionic shifting. That releases the calcium ions. They bathe the contractile proteins. That swings a protein, a molecule called tropomyosin out of the way of a binding site on the filaments, and so therefore they bind, and then ATP is used to pull those fibers across each other, much like oars in a boat that would pull the boat across the water. Same sort of analogy, if you like. That's how that works. Every single twitch of every single muscle fiber that ever contracts is therefore a complete 100% contraction and relaxation thereafterwards. And it happens at full force for that muscle fiber. Okay, there is no moderation of the force at which any given individual muscle fiber contracts. They all do it 100% every time, and they all contract fully and relax fully thereafter. It's called the all or nothing concept. That's how muscle fibers work. Now that brings up a point or a question that people usually ask at that point, which is, well, hang on, we can contract our muscles faster or slower, and we can do so more forcefully or less forcefully. How is that so if every single muscle fiber contracts fully and at full force every time? Well, basically there are two methods by which the human body and the body of other animals with skeletal muscles actually achieve this. And it's pretty simple. Not every muscle contraction will activate every single muscle fiber within that muscle. A muscle fiber, depending on which muscle it is, can have hundreds, thousands, tens of thousands, or indeed hundreds of thousands of individual muscle fibers, individual muscle cells within the cross-sectional area, I guess, of that muscle. Not every muscle contraction recruits or causes every one of those muscle fibers to contract. Usually muscle fibers are arranged into motor units, A motor unit is a number of fibers, be that 1, 2, 5, 10, 100, or 1,000, depending on the size of the motor unit. And all of those fibers in that unit are connected, if you like, in parallel, and they all contract fully and completely, or not at all, if that motor unit is activated by the brain. And if that motor unit is not activated by the brain, then that muscle, that motor unit does not fire, and those fibers do not fire. So if your brain says, I need to pick up this ring off the desk, that just recruited very, very few of the muscle fibers in my arm and shoulder and other supporting musculature to initiate and to make that happen. This doesn't weigh much. There's not much resistance. I didn't need to contract very many of my muscle fibers to pick that ring up at all. If that ring was a brick, different story, yeah? If it was a 1 ton weight, I could contract all my muscle units, recruit the whole lot, at least the ones that my brain has learned how to recruit fully and completely, and still not move it, because I wouldn't be able to overcome the resistance. Yeah, makes sense. So motor units, very important. Not all fibers contract in every contraction. That's a way of moderating the force. How do we moderate the velocity at which a muscle contracts? Because I can either pick that ring up very, very slowly, or I can pick that ring up very, very quickly. Different sort of speed of muscle contraction, yeah? How does that happen? Well, that depends on the fiber type differentiation, okay, which is really the main point of this discussion today. Here is a table, a chart, which talks about 3 different categories, broad categories of muscle fibers that we possess. They're called type 1, type 2A, which is also sometimes called 2X, and type 2, or sometimes called type 2B. Basically, the difference between these muscle fibers, there are several differences between them on a gross morphologic level, i.e. how they're constructed, how they're put together, what kind of proteins, contractile proteins are in them, how do they express different chemicals, different enzymes, what are their rates of abilities to do various different aspects of those gears in that gearbox, the different, glycolysis and PCR and aerobic metabolism, how are those things all balanced out in terms of an individual muscle fiber, and also in the speed at which a single twitch occurs. A type 1 fiber might twitch, this is an analogy, obviously there's an actual timing, but quite slowly. An intermediate fiber might be twitching like so if it twitches, and obviously a type 2 or 2B fiber really, really fast. So that's a way of not only moderating the contraction rate, but also the force, because type 2A, 2X, and 2B fibers are also much bigger in cross-section. They're much more powerful, they're much stronger. They are able to overcome much larger resistances, and so they are also recruited when you're picking heavy things up, as well as when you're picking up light things and you want to do it quickly. So that's kind of how all of that pans out. So let's have a look at some of the different characteristics of these muscle fibers. Type 1 fibers generally appear red. Why is that? It's because they contain a lot of a protein called myoglobin. What is that? It's the muscle equivalent of hemoglobin, which you'll find in the blood. It's the oxygen carrying pigment that is a store for oxygen. It is able to absorb oxygen from hemoglobin and store it in its own store inside the muscle in myoglobin. That's very important for a type 1 fiber, which has very little glycolytic ability. It's mainly an oxidative fiber, therefore it's not very powerful, it's not very big in cross section, it doesn't contract quickly, so it needs a lot of oxygen buffering, oxygen containing ability, so it looks red. Type 2A or 2X fibers look kind of either white or red. Sometimes people call it pink. You'll notice, for example, examples of pink meat are things like pork, humans the same, actually, mostly, because we actually have primarily type 2A or 2X fibers, not so many type 1 in general, and not so many type 2 in general, although we do have some, and different muscles have different makeups of fiber types, which I'll talk about soon. A type 2 fiber is white, that's the white meat, that's the stuff that has very little oxygen holding capacity of its own. It's largely glycolytic. They're usually much bigger, much more powerful muscles involved in either very rapid or very powerful muscle contractions, overcoming a lot of resistance or overcoming moderate resistances very rapidly. You'll find them in flight muscles in birds, obviously. You'll find them in fish, those kind of things, largely. But also humans have some white fibers, depending on the different muscle and what the role of that muscle is. And also there's a genetic influence there as well. So obviously, to follow that logic through still further, in terms of the oxidative enzymes, obviously in the type 1 fiber, there's a high concentration of those, medium in type 2A and low in type 2B. That follows, that makes sense. The myoglobin content, we've kind of talked about that. That explains the color differences in terms of how they appear. A glycolytic capacity, the ability to undertake glycogenolysis. Obviously, if you follow that through there on the chart, the logic there is clear on that as well. Same deal with mitochondrial density, very, very high in the oxidative fibers, medium in the middle fibers, low in the faster, more powerful fibers. Why? Mitochondria are the oxidative organelle, so that makes sense. Capillary density, okay, that makes sense as well, because what do capillaries do largely? They deliver nutrient and oxygen largely. So, yep, there's that. Calcium turnover abilities, that makes sense if you understand what I was saying about calcium being the thing that needs to bathe the contractile proteins to get that happening. Myosin ATPase, again, myosin is the thicker, the actual powerful contractile protein element of the two actin and myosin. What you find is that the myosin ATPase is associated with is the thing that moderates the rate of glycolysis within the fiber, so that makes sense that it's high in the white fibers, high to medium in the pink fibers, and low in the red fibers. Yep, cool. The same deal with phosphocreatine stores, makes sense. Fiber diameters large in the white, powerful, fast twitching fibers. Intermediate ones are intermediate, type 1s smaller, Contraction speeds, high, moderate, then low. Force capacity, high, moderate, and low. Fatigue resistance, low, medium, and high. That makes sense because the amount of time that you can maintain glycolysis is very limited, because our ability to store to store glycogen in our muscles is very limited. Why is that the case? It's the case because muscle glycogen involves water in its structural makeup. Water is very heavy. It's about power to weight ratio. The more glycogen you store, the bulkier, the heavier your muscles are. So the more of your own body mass weight that you have to overcome in order to use that energy. So that there is a point where it becomes a lack of continuing returns, where we can't do it. So the body has an upper limit on its ability to store glycogen, and thus that's why we evolved as hunter-gatherers who are designed for fast, powerful, short, sharp actions, and then rest, burst, rest, burst, rest, burst, rest. That's how we're designed. That's why, that's the first reason why the long, slow distance training is not such a good idea. Let's have a look at a cross-sectional slide through some muscle. This is rat muscle, but it doesn't matter. It's very similar to human muscle fiber makeups. What they've done here is they have stained different muscle fibers within this cross-sectional muscle area here. They've stained them for glycogen, basically. So the more glycogen that is involved there, the different colors that you get. So you can see type 1 fibers there. Look up here, white, very little glycogen involved there. And then you've got the 2A and the 2B type fibers there. There's different nomenclatures from different people on how they actually name these things. This might be a bit confusing in terms of the names here. 2A or the 2A or 2X thing that was on the previous slide is a different nomenclature to what's here. Don't get too confused. It's basically you've got increasing muscle fiber diameter there and increasing power and all that kind of stuff there. That should be quite clear in terms of what we're looking at. So that just kind of supports the theory that we do have these kind of three different sort of muscle fiber types. Strictly speaking, it's not that a muscle fiber type is this type or that type or that type. It is actually a continuum. Basically, the type 1 and the type 2 at either ends of the spectrum are the kind of extremes of what that particular animal or that particular individual is able to express in terms of how those muscles are morphologically, what the enzyme expressions are, how much of the big chain versus the small chain myosin it has, etc., etc., etc. And all the other fibers are kind of intermediate in between the two extremes. And I guess it's important also to understand that in the untrained state, the fiber makeup within each individual specific muscle in your body depends on the location, the role, the size of that muscle. So examples are the soleus gastrocnemius muscle. Obviously, the soleus is a slow twitch, fatigue resistant stabilizer postural muscle that works all day every day, that we're on our feet and moving around and walking and stuff. It's got largely small oxidative red fibers and it doesn't fatigue so much. It keeps doing what it's doing. To get that powerful flexion, or plantar flexion, dorsiflexion action going at the ankle joint, the gastroc muscle is what's involved there. It's a powerful muscle. It's a fast twitch muscle. It fatigues quickly. There are many more of the glycolytic fibers and much fewer of the oxidative fibers. It's a pink to white sort of muscle. Two muscles, same place, different jobs around the same joint, but quite different fiber type makeups. So that's the first thing. Different muscles, different fiber type makeup. That makes sense. Also, across the different muscles in any given individual, in the untrained state, your fiber makeup is genetically influenced as well. Some people have genetic advantages in some particular muscle fiber makeups. For example, we can look at Mo versus Usain, for example. Would Usain be a good distance runner? No, he'd be absolutely shit at that. Why is that? Well, because his muscles are largely fast twitch, and so he has that genetic advantage. He's trained that still further, so no, he wouldn't do well in endurance running events at all. Mo, while he would do very well in endurance events and does, he does very, very poorly if you put him on a sprint track against, for example, someone like Usain. Obvious. Okay. So genetic makeups, genetic advantages, genetic predispositions, whatever you want to call it, they exist as well. The fiber type makeup is also trainable. In other words, as you train, so shall you perform. As you use your muscles, so your muscles will become. Your motor units will be recruiting different motor units in such a way, and your body will learn what you are asking it to do chronically across time. And those intermediate fibers between those two extremes are plastic in their nature. They will change their myosin light chains to heavy chains if you do a lot of resistance, burst and rest type activity. They will drop the oxidative ability down, they will get the glycolytic ability up, they will become bigger. And the reverse is true if you do long, slow distance cardio type training. In other words, they will get weaker, they will get smaller, they will become more oxidative, will become less glycolytic. That will have influences on your muscle mass. If you do a lot of cardio work, that will reduce your muscle mass. Want any proof of that? Again, look at the body type of Mo versus Usain. What have you got there? Okay, that is a trend. Although there was some genetic influence there, absolutely, a lot of it trainable as well. And the same is true of any given individual. You can train your muscle fiber type to become more glycolytic, bigger, or you can train it to become less glycolytic, smaller. So effects on your functional strength, your muscle mass, your lean body mass, your metabolism, your ability to metabolize and cope with carbohydrates, effects on your insulin resistance and therefore on your inflammatory situation and therefore on diabetes, heart disease, obesity, etc., 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 etc. Basically, all in all, it paints a picture of we are not genetically designed to undertake activity for long periods of time at very low intensities. That causes our muscles to train in such a way that is deleterious to our overall strength, functional health, metabolism, and generally it's just not a good thing. Cardio should never, ever, ever be undertaken, especially if you're trying to get stronger, especially if you're trying to lose body fat, because one of the sure ways of getting fatter would be to reduce your muscle mass and therefore reduce your resting metabolic rate. The inverse is true about getting bigger muscles. So yeah, basically cardio is bad stuff. But we need that for our health, our heart health, don't we? Well, no, because as I've said, the energy systems are integrated, they are gears. At the high level, you are activating that system fully. A really good heavy resistance set will get your heart rate up just as high, if not higher, than long, slow distance type training. Although it'll drop down again while you're resting before you burst it back up again for your next set. Actually, if you average the heart rate across time, you'll find it's the same work. And so there is just no argument whatsoever for long, slow distance aerobic type cardio type training. It's bad, it's nonsense, you shouldn't do it. I'm not saying you should never exercise in that mode ever. I'm just saying you shouldn't have it 3, 4, 5 times a week, 2, 3 hours at a time, and that's your training, because that's just nonsense. That's ridiculous. That will do you harm, both physically and metabolically, and also probably mentally. And also, you will find that there is quite a significant risk of a thing called sudden cardiac death syndrome, which can occur in people who largely undertake such long, moderate to low intensity cardio or aerobic type training too much. So not a good thing overall.